everybody. My name is Christina Besla. I'm the chair of the Astrophysics program, and it is my pleasure to award this prize that goes to our graduate student for who's given the most exceptional, who's created the most exceptional theoretical research project paper for the past year. This is a prize that's awarded annually, and so today to Eonho Chang. Congratulations. Eonho's a graduate student in applied physics and is working with Dr. Andrew Uden, who will give him an introduction.
Yeah, hi. Congratulations again, Eonho. So yeah, I'm Eonho's advisor. I've worked with him on this project and the work we've been doing. So I don't want to say too much because he's going to tell you all about it. But I think as not just as theorists, obviously, but as scientists in general, we try to do work that is related to cutting edge observations and things that are new because, well, that's what people are excited about and that's how you can make progress. But then maybe especially as theorists, we also like working on classical problems, right? And those can sometimes be a lot harder to make progress on because people have been hammering at them for a long time. And so in this case, the sort of new observations are a lot of the observations of exoplanets in formation, in particular observations of protoplanetary disks by ALMA. And a lot of the classical physics that's involved here is the study of hydrodynamic shear instability, which is a broad problem in planet formation, broad problem in fluid dynamics. And when it's applied to astrophysics and disks, it's known as the Rossby wave instability. And so what Eonho is going to describe is ways where this fundamental fluid dynamical work is being used to make progress in understanding planet formation and related observations. So take it away, Eonho.
Thank you for the kind introduction. Right, today I'm going to talk about what I did to receive this award. Basically, my work on Rossby instability, and we're going to talk about vortices, shear instability today in the context of planet formation. Right. So I have three things prepared. One is the brief overview on planet formation, protoplanetary disks, dust traps, shear instability, and the second part is the work I did on fluid dynamics, shear instability. Then the third one is what I'm going to do, what I'm currently doing to improve on the current study. Right, so as a brief overview, I want to talk about the process of forming planets. We have these molecular clouds, sheets, filaments, and cores, and pressure is fighting gravity, and at some point gravity wins, starts to collapse. As it collapses, the radius shrinks. That means you rotate faster and faster to conserve angular momentum. And the next stage is you have a central object, protostar, shrouded by an envelope. It's accreting material through the equatorial region, next material in the polar region. The next part is you have a envelope dispersed and a clear disk around it. And then in this disk, you form the planets Jupiter, Mars, and Earth. Right. So in today's talk, we're going to focus on this D part, the protoplanetary disk. And here's an observation with JWST that is recent of an edge-on protoplanetary disk, basically a composite image on 3 different wavelengths. So that's how it looks like an edge-on. But how do these disks look like face on? So in order to do that, I need to talk about the different phases of protoplanetary disks. Going from class 1, 2, 3, basically it goes from more spherical to disky to nothing. And we're going to focus on class 2 disks. And this is what does two disks look like face on, observed with ALMA in Chile. So if you're seeing these disks for the first time, I think they're awesome. So one thing that strikes out to me is that they're so symmetric. They have rings and gaps, are concentric, alternating. So why, how are these rings formed, right? So to explain that is to go back to this fundamental idea that gas is moving differently from dust. So as a result, dust drifts to high pressure regions. So if you take this monotonically decreasing pressure profile, right? Higher pressure near the star, decreasing away from the star, the dust particles will drift inward. So if you look at this disk, oh, okay, then that's what happened. The dust disk used to be larger, but then they drifted inward, so now it has a more compact sized disk. But if you have a more complicated pressure profile, like here, you have two bumps, then the dust particles, some of them will still drift inward, but some other ones will get trapped in these pressure maxima. So if you look at this kind of disk where it has two rings, then this is the explanation. Okay, the dust drifted inward, but also toward the local pressure maxima. Okay, so that's how these rings are explained, but who cares? Well, it looks like, right, we think these dust traps play an important role in planet formation. So as you might know, we have to go through many orders of magnitude, from microns to thousands, tens of thousands of kilometers. And we think we understand relatively well, going from microns to millimeters, from lead experiments and whatnot. And I think we have some grasp of going from kilometers to planets, planetesimals to planets. But the major challenge here is the meter size barrier between millimeter to kilometer. This happens because the dust grains start to drift faster, actually fastest around millimeter. And as someone said, if you throw a rock at a rock, they'll break each other, not stick to each other. So it's a challenge, but if you have a dust trap, then you can prevent the dust grains from drifting inward and get fed to the star, and increase the local density of dust for what's called the streaming instability. I'm going to explain it in a second. And with this dust trap and streaming instability, we can overcome this meter size barrier. So what is streaming instability? I'm showing here a simulation of streaming instability done by Dr. Lee, who was a graduate student here at Stewart. Right, so basically what streaming instability does is take this millimeter size, centimeter size grains and concentrate them to high density so that they are gravitationally bound. Basically planetesimals, the building blocks of planets. Right, so in that sense, dust traps are important.
Sir, question?
Yes?
The previous picture, that was in the plane of the disk?
The pretty picture. I have a lot of
Previous picture.
Previous picture.
The X and Y, were those in the plane or
Ah,
was one perpendicular to the plane?
that was, I think, azimuth and radius. We're talking about this
Okay,
one?
okay.
X is the radial and the Y is the azimuth, but it's a local shearing sheet or shearing box. So it's Cartesian. Yeah. And right, I'm gonna move on to the research part, and I wanna do a short experiment. Might be the most fun part of this talk.
sorry.
That way. So what I have is a bucket with a little bit of water, an inch of water. Put some use tea or tracer. More tracer than that. Okay. I'm gonna basically rotate this. Let the string has enough tension. What happens in the bucket? Oh, that's strong enough. Well, you don't see anything here, but for this kind of scenario, I prepared a recording. What you're supposed to see is this. Well, oh, I'm not sharing my screen, am I?
You are. I think you just clicked on the different input on the desktop. Yeah.
Change back to this.
I think remove pin on your stuff.
Oh, yeah.
Stop the phone. Stop the phone.
Stop the phone.
Switch to shared content.
Upper left corner.
Yeah, the upper left.
Yeah,
corner.
on the
The
upper left
remove.
corner on the desktop, there's a switch to shared content pin. Not there, but if you keep going left, down, that thing might do it.
Okay.
Ah, okay.
Yeah.
Thanks. Right, yeah. Video won't play. There we go. This one is a successful experiment where you're supposed to see vortices forming.
Oh, nice.
It's a shame I couldn't show you live, but yeah. So what's happening here, right? This is a velocity profile. The moment you drop the bucket, so you have this huge velocity gradient, and it's clearly this part that is related to vortex formation, right? This huge shear. So that's what I wanted to show. Right, and you know what else have shear? Disks have shear. Why? Because the star's gravity, basically star's gravity. Near the star, you orbit faster. Away from the star, you orbit slower. So you have this shear. But unfortunately, this disk does not form vortices. And the usually quoted criterion is called Rayleigh criterion, where this kappa squared has to be greater than 0 everywhere. What is kappa? Kappa is radial oscillation frequency or epicyclic frequency. Basically tells you if you have a nearly circular orbit, you can approximate it as a circular orbit with a little bit of radial oscillation. Kappa is the frequency that characterizes this radial oscillation. And why do you care about this kappa squared being positive? Well, kappa squared being positive means kappa is real. Kappa squared being negative means kappa is imaginary, which is a bad news for frequency, right? Because it has exponential growth instead of oscillating. But that's for a strictly Keplerian disks, and pressure actually changes the motion of gas, so it affects the shear that is felt by gas. Basically, by this equation, you have actual orbital frequency that is Keplerian and modified by this pressure gradient. kappa squared is still a function of actual orbital frequency, not the Keplerian. I have here some examples of pressure profiles. One, you can see that only one of them is trapping dust, right? You need pressure maximum to trap dust. The other two don't trap dust because they are not maximum. And I can translate this pressure gradient profile to kappa squared profile. NR squared is just another radial oscillation frequency. It's small, we're going to ignore that. But as you can see here, the one that traps dust also has the most reduction in this kappa squared quantity. And we want kappa squared to be away from zero if we want stability. So this says strong dust traps tend to be unstable. Here's some simulation that wants to play as well of two kinds of dust rings. One's stable, one's not. I'm plotting dust density over gas density. The left one is stable, it stays as a ring, but the one on the right, it's not stable, it forms, well, it's not clear what forms here, but we stop that. So at some point, you stop the simulation and look at the snapshot. You have a ring and two vortices. So this is basically the Rossby instability. It's a radial shear instability that forms vortices, just like the bucket. And it has implications for the ALMA rings, right? So the rings we see are stable to IWI, so they stay as rings, whereas the crescents, vortices formed by IWI. And the major question here is, which rings become unstable? And how do we know if a shear is unstable or not? There are some classical results regarding this. Here's a velocity profile. There's a wall at the bottom, and the velocity is increasing, going away from the wall. There are a bunch of other shear profiles, velocity profiles. And which one of these are unstable and form vortices? Well, there's this old criterion, sometimes called Loveless criterion or Rayleigh-Fortov theorem, depending on who you talk to. Basically says you need a potential vorticity minimum. And according to this necessary criterion, the upper four are stable, and it's only the bottom two that are possibly unstable. But it's a necessary criterion, so we don't know if it's unstable or not. And there's also a sufficient criterion for instability. We saw that earlier. It's the Rayleigh centrifugal criterion that this kappa squared is negative, right, somewhere. Then how useful are these criteria? So I'm plotting here the necessary criterion. It's going to show up as I play the movie. The sufficient criterion at the bottom. So I'm plotting the kappa squared profile of this disk. Play the movie. So the necessary criterion is immediately satisfied. It tells me this could be unstable, but I don't see any vortices yet. So when do the vortices come? About now, you start to see vortices developing. So right about when this kappa squared quantity, the minimum of it hits the half value, the vortices are formed. So it's you can see that the necessary criterion and the sufficient criterion are not very useful for describing when the vortices form. So that motivates the need for this study. It's that there's no necessary and sufficient criterion for the vortex formation. And we saw that either happens somewhere in between, but we don't know where exactly it is. The necessary criterion and sufficient criterion, neither of them are good indicator of vortices. Right. So here's just a slide with equations. What I use, I assume thin disk, inviscid, there's no viscosity, no magnetic field, no self-gravity of the disk. It's described by 2D Euler equations. You have continuity, momentum, you have star's gravity and pressure gradient, and the energy equation written in terms of entropy, and the ideal gas law to close the equations. So what I'm going to do is linear stability analysis. And if you're not familiar with that, it's basically when you have a ball on a hill, give it a nudge, it's going to go down the hill. Oh, it's not much. Whereas if a ball is in the valley, give it a nudge, it's going to oscillate. And this is an analogy for the ball rolling down the hill, that the ring goes away, whereas the ball in the middle of the valley is that the ring is stable to nudges. It's stable, so it stays. So basically, linear stability analysis boils down to, okay, is the equilibrium resilient to small perturbations? And the problem here is that we don't know the landscape beforehand, if it's stable or unstable. So we linearize the equations of motion by assuming this dust trap profiles, right? You have many different shapes of pressure, and we give it a nudge. F1 is the perturbation, and we assume this Fourier modes, where m is a positive integer, omega is a complex frequency. So the real part of that would mean it's a wave. The imaginary part of that would mean it's an exponential growth or damping. We're going to focus on the growth case because that's what makes the vortices. And one of the tedious parts of this problem is that you have to solve a second order boundary conditions, which is not the case with other kinds of instability like MRI or Chomry's gravitational instability. So here are some results. Right? Basically, I'm showing here different pressure profiles. Horizontal axis is the width of the pressure bumps, and vertical axis is the amplitude of the pressure bumps. And you can see that in general, it's the sharper ones, small width or larger amplitude pressure bumps that trap dust. I'm going to show another one here. So that was for the dust trapping criterion. Whereas for this one, we're looking at if the bump is stable to the RWI or not. So it's also the ones that trap the dust more unstable to RWI, right? The sharper ones that are unstable to RWI. But we want the dust rings to be stable. And that means the overlap of these two regions indicate the dust traps that can survive the RWI. So based on this result, you can state that the dust trapping features have width larger than a scale height. H is the scale height. And now I move on to this Awardee study, halfway to Rayleigh criterion. It was published last year. And basically, this is about taking one step further what we did here. Because other people have studied RWI, but they didn't really have like they didn't provide the general criterion for triggering the RWI. So the purpose of this study was to, okay, maybe we can simplify the problem and get the general necessary and sufficient criterion for RWI. And another part of simplifying problem is that you can explore broader parameter space. And what we did is go to the simplest possible case, reduce the problem down, and gradually build up the complexity. So the simplest possible case is locally incompressible. Then we go to local compressible, relax that incompressible condition. Then we get back to global compressible. Right. So the local model is the shearing sheet, which is just right. You have a disk and you're zooming on a small patch of disk. So you discard curvature. So your shear is linear instead of being a power law. It's a classic result from Goldreich and Lyndon-Bale. And this problem is very similar, as Andrew noted, to classic fluid dynamics problems. And another simplification we do is use enthalpy instead of pressure. So enthalpy, what is enthalpy? Well, basically you can define enthalpy as this relation between pressure, density, and enthalpy. It's just that the thing you have to describe with density and pressure, you can just describe with enthalpy. So one less parameter. And the shear, or the velocity profile in the shearing sheet is simplified as well. It's just linear. And we assume adiabatic also to drop temperature. And we have just two parameters, amplitude and width of the enthalpy profile. So we had a bump, just like the pressure bump case, we have an enthalpy bump that causes change in the velocity profile. And we consider other profiles as well, not just the bump, gaps, jumps, and drops. And we do the same thing as before, linear stability analysis. Use linearity equations, use these bump profiles, gap profiles as equilibrium, perturb it a little bit, and assume this particular form for the perturbation. If we want to look at solutions, look at perturbations where it's growing exponentially, so S is positive. And here's a result from the local incompressible shearing sheet, the simplest possible form of this problem. It's the same as before. I'm showing width on the horizontal axis, or you could also think of it as a perturbation wave number. And the vertical axis is the amplitude of the enthalpy feature. And you see the same trend that sharper ones, smaller width or larger amplitude enthalpy profiles, they are unstable to RWI. And I'm also plotting another region here for the sufficient criterion, right? And kappa squared is less than 0. That's the gray part. Again, it's not a good indicator of RWI stability boundary. And the necessary criterion is not very useful because it doesn't even show up in this window. It basically the negative infinity. I just said that. Oh, one thing we one of the insights we get from this simplified analysis is that we analytically recover this scaling that was only empirically measured before. And you can repeat this for other shapes. We get the similar result. Moving on to compressible shearing sheet, you have an additional parameter KYH, which you can think of as a compressibility. where KYH is less than 1, is compressible. Right, and I'm showing here different compressibility curves, RW boundary of different compressibility. As you can see that as you decrease KYH, the boundary moves up, meaning it becomes harder to trigger RWI. So, and another interesting insight from this compressible shearing sheet is that as you decrease KYH, it looks like the RWI boundary approaches this asymptote, where this kappa squared, the minimum of it is approximately equal to 0.6. So that becomes a good indicator of RWI stability. That's going to lead to the criterion I'm going to describe soon. And now I move on to from compressible shearing sheet to compressible global disk. And what you find here is that, right, plotting here, the local model is dashed lines, and the global model is solid lines. And these two agree with each other. The feature width is small, basically less than aspect ratio or the scale height. But as the feature width goes over a scale height, these two models disagree with each other in that the global model is more unstable than the local model. It becomes easier to trigger the instability. Right. And this has implications for dust strength stability in that you study dust strength locally, they might be stable, but if you go to global, they might not be. Here's some other insights, but here's what I want to write. Basically, the title of the talk: halfway Rayleigh condition. So what I'm plotting here, I'm plotting this value of kappa squared along the RWI stability curve. Right. And if you remember that dust trapping features have W with greater than scale height, right? So I'm shading that here as well. We can just read off what the values are. This kappa squared minimum from this plot, it's around 0.5, 0.6, so halfway, right? Because kappa squared being 0 is really instability. Right. So it's not really exact, as you can see. We've tried a bunch of other models, bumps, gaps, local and global. They agree with each other a lot for smaller widths, but they start to diverge at large widths. But they are approximately in the same ballpark. So, right, this is approximate, but the strength of this criterion is that you can easily evaluate it. The only thing you need is just the orbital motion, the gas velocity profile. Then you'll be able to know if it's stable or unstable to IWI, form vortices or not. Oh, this is not supposed to be there. Right, so back to the dust rings. Do we know, now that we have this insight, this halfway to Rayleigh criterion, do we know these rings are stable or not? Well, I don't know, that's the short answer. But what's happening is that the gas observation data is not as good as the dust observation data. So I'm showing here the top panels are gas. The small square is the size of the dust observation at the bottom row. So right, it's hard to compare, right? The resolution for the dust observation data is much better than the gas one. So this is on hold until a better gas observation is available. But here's what I'm doing currently, basically including planet to the equation. This is a simulation of a planet going around the star, carving gap in the gas. As you can see in this azimutally averaged profile here, right? The horizontal axis is the phi azimuthal direction, vertical axis is the radius. You have the spirals and whatnot. And the cool thing about this is that as the planet carves gap around this, right, it triggers vortices. It is the gap profile becomes unstable to RWI, both inner and outer, and this can affect the migration of the planet. You can see it started from 1, but it's moving inward slowly now. So what's happening is planet carves gap. The disk responds by torquing the planet. That changes the radius of the planet. But at some point, the disk is unstable to RWI, and it triggers vortices. And what the vortices do is also affect the, provide torque to the planet and affect the migration. So it's a very interesting problem. And I want to end with applications in other disks, not just protoplanetary disks, because other disks also have shear. And the original theory for IWI was initially developed in galactic disk context. In a recent paper brought to my attention is this, black hole accretion disk can also trigger IWI. They can have these vortices, and the coherent signal from this, the gravitational wave signal, is something you can detect. That's what these authors argued. So you might have some application for other disks. And here's my summary slide. Protoplanetary disks have pressure bumps that are larger than a scale height of the disk. Those are the ones that are stable. That would explain these rings on my disk. You can use this halfway to Rayleigh criterion, which is approximate but easy to evaluate, to assess if a disk is unstable to RWI or not. And maybe this is relevant for other disks, not just protoplanetary disks.
Thanks a lot, Eonho. And yeah, we now see why we're doing theory and not experiments in our. But yeah, does anyone have any questions?
So you mentioned at the very end that's how these instabilities can occur in accreting black holes, and you showed a simulation from Orgoclib where it's a stellar mass black hole, although it's GRMHD, so it's probably scale 3. Like, couldn't these happen also in AGN disks? And how much mass can you put then in the unstable vortex in that context?
Right. I think. Right. So the theory for IWI is developed in the context of thin disks. I don't know how thin AGN disks are. Also, this does not have magnetic fields, so MHD might have something to do. Although you could include non-ideal MHD, so that would tone down a little bit.
I want to say this simulation, I think, actually does include magnetic fields, which is why it was an exciting result. Because I wrote a whole paper about how when you include magnetic fields, you can't get good gravitational waves from accretion disks. And then they were showing an example where maybe you can. So I was like, oh, good.
I was just to add to that people have studied the interaction of magnetic fields with RWI and protoplanetary disks as well. But it's often that, it depends on whether it's ideal or non-ideal MHD, whether the magnetic fields prevent this from occurring or not.
So in this linear analysis you did with the fluid equations, are you modeling the gas as a fluid or the dust as a fluid?
It's right. It's just one component. It's just the gas. I'm not including any dust to gas interaction. So in that sense, it's lacking, right? For a complete picture, you want to couple both gas and dust. But for simplicity, I omitted the dust.
So then is the story then that you have these thin rings in the disks, they become unstable, and then the dust coalesces inside the vortices? Or is it that when they become stable, that's when you get planetary formation?
Right. So, right. What people think is both in the dust rings or and in the vortices, you can form planetesimals because both of them can collect dust in the vicinity and reach high density.
Have you made, so what you say in terms of the gas not having sufficient resolution, so what exactly is the observational counterpart that you're looking for?
Right. So I think I have a backup slide for that. Basically, when you, right, I want to look at the bottom figure. Basically, you're comparing the dust structures to gas structures and how well they align together. As you can see, 100% is the best, but none of them reach that well. Most of them reach 20%, 40%. So there's not a very good agreement right now. I think that's because there's insufficient resolution for the gas, spatially speaking.
Yeah, it's essentially cost, right? Dust continuum is much cheaper than doing narrow line observations. So just get the observational time required to get the resolution. It's just vastly more expensive. But there are ongoing ALMA large programs to try and make progress in this.
Yeah, this is what I'm
So
wondering. It's like,
we're
is,
looking forward to it.
yeah, exactly. Like you've got a case here now pushing forward for the theory needs these observations. Like, is your focus now to start working with some of the observations? Try and help make this argument so you can get the data you need.
That's a great idea.
Yeah, the Larian thing, know what we've done. Yeah, yeah. All right. Well, if there's no other questions, let's congratulate Eonho again. If you want to come up.